All right, unit circle. First of all, our special right triangles, I had just started and then remembered to start recording. So 30, 60, 90, you have half of an equilateral triangle. So the side across from 30 is half the hypotenuse. Pythagorean theorem will give you that the side across 60 is the side across from 30 times root 3. For the 45, 45, 90, if the angles are equal, the legs are equal. So if this is length B, this is length B. Through Pythagorean theorem, we can find that the hypotenuse is B times the square root of 2. Now, what I want you to do is write the ratios of each of these special right triangles and simplify them. So be ahead of me. If I do this for you, you're going to have a harder time remembering these numbers. So the sine of 30 degrees. Sine is always opposite over hypotenuse. So when I look for 30 degrees, there it is. The opposite side is A. The hypotenuse is 2A. And what does that simplify to? 1/2. All right, now, still on 30 degrees, what is the cosine of 30 degrees? We know that cosine is adjacent over hypotenuse. And when 30 degrees is being used, this is the adjacent leg. And I get A times the square root of 3 divided by the hypotenuse 2A. The A's cancel, leaving me with the square root of 3 over 2. So we have 1 over 2, and we have the square root of 3 over 2. I'm going to move over to the 60-degree angles because of how quickly this is going to go. When I change from looking at 30 degrees to instead looking at 60 degrees, the hypotenuse is still the hypotenuse, but opposite and adjacent swap. So with 60 degrees, this leg is helping to make the angle and it is adjacent. This leg is opposite. So when I do the sine of 60 degrees, I'm getting opposite over hypotenuse, which simplifies to root 3 over 2. And yes, same exact thing as we got right there. The cosine of 60 degrees adjacent over hypotenuse is A over 2A, which reduces to 1/2, just like this one. Now we're going to do the 45-degree angles, and it's going to go fast. Pick either angle, doesn't matter which one. Opposite over hypotenuse for sine is going to be B over B root 2. That simplifies to 1 over root 2. And do you see that cosine is going to give you exactly the same thing because opposite and adjacent happen to be the same length. Now, to make these numbers easier to remember, we're going to simplify the 1 over root 2 by multiplying the fraction by root 2 over root 2. That turns it into the square root of 2 divided by 2. Why does this make the numbers easier to remember? Because now the numbers are 1 over 2, root 2 over 2, and root 3 over 2. These are the only numbers that are coming out of the sine and cosines of the angles of my special right triangle. And do you see how it's basically just like going 1, 2, 3? In fact, if you really wanted to, square root of 1 and 1 are the same thing. So it's the square root of 1, 2, 3 over 2. Now, we're going to come back to that. But temporarily, we're going to talk about how our circular motion that we learned about, that you'll be quizzing on tomorrow, how that circular motion relates to right triangles. We start with a right triangle in quadrant 1. We put one of the legs on the initial side, which is 0, and we make the hypotenuse be the terminal side of an angle. So I've got an angle that is moving with a positive rotation counterclockwise from 0. Now, the unit circle is called the unit circle because the hypotenuse is 1. And with the hypotenuse being 1, a lot of numbers come out really nicely. However, we don't have to work with a circle of radius 1 all the time. It's just this is a really nice reference because whatever the radius is, we can just multiply by it to everything that we know. So we start off with this base knowledge, but a lot comes out of it after we learn this base knowledge. So here we go. This right triangle, we have a hypotenuse that we know is length 1. We have 2 legs. This one is adjacent to the angle. This one is opposite the angle. We know that the sine of an angle in a right triangle is opposite over hypotenuse. If the hypotenuse is 1, what does that mean the sine of theta is equal to? The sine of theta is equal to this length right here. So guess what's going to happen with cosine theta? Cosine is known to be adjacent over hypotenuse. Well, if we're looking at a unit circle, the hypotenuse is 1. So that means that cosine is the same as the length of the adjacent side. That means this distance is equal to the cosine of the angle. This is a very big deal. Now, this point, x comma y, I want you to realize that if we back off from the circle and the triangle a little bit, what we see is an x-axis and a y-axis. And every point has an x-coordinate and a y-coordinate. What we're going to focus on are the points that exist on this circle. So I'm going to draw a circle, just a little, to be a point. Whoa, oh, it was highlight color. Didn't mean to do that. Okay, circle. I wanted it to be filled in, but whatever. Just, this is supposed to be a point. This isn't working out the way I thought it would. But anyway, we're looking only at points that are on this circle. each of those points has an x-coordinate and a y-coordinate, and that x-y coordinate pair happens to be the cosine of the angle that has been traversed, comma, the sine of the angle that has been traversed. And we can go beyond the right triangle. The right triangle only gets to deal with angles between 0 and 90 degrees. The right triangle kicks it off, but the circle creates the symmetry. Because I can take this right triangle and I can flip it over here, and the same properties are going on. If I mirror this triangle onto the other side, realize that this angle right here is theta less than 90 degrees. Its y-coordinate is the same y-coordinate. They share the same sine value. The x-coordinate is on the opposite side of the x-axis. So for these angles, if these are mirror points, their cosines are the same but opposite signed. And this happens to work for any angle that I go around. When I look at an angle that is bigger than 90 degrees and stops here, if that has the same y level as the point over here, then this angle and this angle have the same value of sine. This angle and this angle have opposite valued cosines. And then I can go on and go into quadrant 3 and 4 on this and do the same thing. Now, these are called reference triangles. I don't like to use reference triangles personally because once you realize the relationship that they have with the unit circle, it's easier to just use the unit circle without the reference triangles. So what I want you to know is when you use the unit circle, you are looking at having a terminal side. I'm going to erase all this so that I can emphasize what I'm telling you. So if I have an angle that is like 240 degrees goes around about that much and stops here. This has a point. The terminal side of the angle intersects the circle at an xy coordinate. That xy coordinate happens to be the same value as cosine theta, comma sine theta. And let me make sure that I clarify that's when I'm dealing with this angle, 270 degrees or 240 degrees is what I said. Now, I want you to notice that we're in quadrant 3, and in quadrant 3, sine x and y are both negative. When you have an angle that takes you from the positive x-axis into quadrant 3, you get a sine that is a negative value, and you get a cosine that is a negative value. And I'm going to teach you how to find those. So what I want you to write down is each x-coordinate on the unit circle is equal to cosine theta. Each y-coordinate on the unit circle is equal to sine theta. And very importantly, this includes the positive and the negative values of those x and y coordinates. Now, let me tell you that we can painstakingly go through a lot of work in each of these 4 quadrants using our knowledge of the special right triangles to see how the sine and the cosine show up as positive and negative in the quadrants they're in. But again, that gets redundant and takes a bit of time. We can use symmetry off of one quadrant. Are you ready? This is super important. You can base everything off of understanding quadrant 1 because a circle is symmetric, insanely symmetric. So here we go. In quadrant 1, this angle right here is 0 degrees. This angle is 90 degrees. If I cut the quadrant in half, that's cutting 90 degrees in half, and I have a 45-degree angle. If I cut the quadrant into thirds, and I'm going to overemphasize my cutting into thirds with longer rays coming out, that's cutting 90 in 3. And what angles does that give us? A third of 90 is 30 degrees. And then this is 60 degrees. And what do you know? There's all our special angles. Now, are there more angles than just 0, 30, 45, 60, and 90? There are a lot more angles. These are our reference angles. They allow us to get an idea of what the values of sine and cosine are for other angles. So if you're dealing with 25 degrees, if you understand how to determine the sine and cosine of 30 degrees, you can just adjust it a little bit to understand approximately what the sine and cosine should be of this. Now, granted, it's an approximation. Now, are you ready for this? Are you ready? This is the origin, right? We're dealing with quadrant 1. On the x-axis, this, I have 3 numbers here. And then because this is a unit circle, this x-coordinate is 1. Now, this x-coordinate is 1/2. This one is root 2 over 2, and this one is root 3 over 2. And then if you go back, I'm going to erase the 25-degree angle because that was just talking about something. So if you go back and you look at what is the sine and cosine of 30 degrees, 45 degrees, and 60 degrees, these match up exactly. So if I asked you, what is the sine of 30 degrees? That is the y-coordinate of this point. Now, the 30 degrees is about the angular sweep to a terminal side. The terminal side of that angle intersects the unit circle at a point. That point has an x and a y coordinate. The x-coordinate of that point is the cosine of the angle. The y-coordinate of that point is the sine of the angle. And what did we find the sine of 30 degrees to be? If you look back, we got 1/2. And that is its y-coordinate. The cosine of 30 degrees is root 3 over 2. If you look back, you will see that, and that is its x-coordinate. 45 degrees, both sine and cosine are root 2 over 2. For 60 degrees, the cosine came out to be 1/2. The sine came out to be root 3 over 2. So know that these y values are sine values. The x-axis gives us cosine. And let me add in that this has an x-coordinate and a y-coordinate of 0. If I am having a 0-degree angle, then my terminal side is the same as my initial side, but it intersects the unit circle right here. The x-coordinate of this point is 1, the y-coordinate of this point is 0. So the cosine of 0 degrees is 1. The sine of 0 degrees is the y-coordinate of this point, and it is 0. Over here, we know that the xy coordinate of this point is 0, 1. The cosine of 90 degrees is the x-coordinate of this point, which is 0. The sine of 90 degrees is the y-coordinate of this point, which is 1. Now, that's quadrant 1. Now, we're going to look at the full unit circle. Are you ready? I have spaces put in here so that we can write some things down. Here we go. You are going to write down that along the positive x-axis, this x-coordinate is 1/2. This x-coordinate is root 2 over 2. This x-coordinate is root 3 over 2. If I go along the negative x-axis, this x-coordinate is negative 1/2. This x-coordinate is negative root 2 over 2. And this x-coordinate is negative root 3 over 2. Oh, and then I forgot to say, this x-coordinate is negative 1. This x-coordinate is positive 1. This x-coordinate is 0. Then we've got the y-axis with the same exact numbers. This y-coordinate is 0. Now, as I go away from the origin, I am going to go 1 over 2, root 2 over 2, root 3 over 2. And then if I keep going out, I hit 1. As I go down the y-axis, I'm using negative numbers. So I get negative 1 over 2, negative root 2 over 2, negative root 3 over 2. And if I go all the way down to the bottom of the circle, negative 1. Now, that gives me all the xy coordinates of every one of these dots that I have on the circle. Now what we're going to do is we're going to write down all the degree measures. If my terminal side crosses the unit circle at this point, that's a 0-degree angle. And let me say again, this point has x coordinate 1, y coordinate 0. That means the cosine of 0 is 1, the sine of 0 is 0. This is 30 degrees. And the xy coordinate, now what's really going on is I have a terminal side of 30 degrees intersecting the unit circle at an xy coordinate. That xy coordinate is root 3 over 2 for x, 1 over 2 for y, and that is the cosine of 30 followed by the sine of 30. 45-degree angle, both are root 2 over 2. 60-degree angle, sine and cosine swap what they were at 30 degrees. And then I hit the 90-degree angle. And at that angle, the x-coordinate is 0, so the cosine of 90 degrees is 0. The y-coordinate is 1, so the cosine of 90 degrees is 1. Now, are you ready to keep going? This is where it gets cool. Are you ready? So, let me remember if I was going to do that. Okay. Just trying to remember what I had planned. So, I've got 2 different cuts. One of them is cutting the quadrants in half with a 45-degree angle. We're going to add over and over again. One 45-degree angle plus another 45-degree angle plus another 45 degrees. 90 plus 45 degrees, 135 degrees. Plus another 45 degrees is going to take me over here, and that gives me 180 degrees. Plus another 45 takes me halfway through quadrant 3. 180 plus 45 is 225 degrees. Another 45 degrees gets me to 270. Another 45 degrees takes me halfway through quadrant 4. 270 plus 45 gives me 315. And then if I add 45 degrees one more time, I find my way back to 360. And if I wanted to, I could keep going. And I could get that on my next round, it's 360 plus 45 degrees, which is 405 degrees. But we're not going to do that. I just want you to see that you can keep doing this as many times as you need to. So you can actually use multiplication. You can look at 1, 2, 3 times 45. 1, 2, 3, 4, 5. 5 times 45. Now, the other way that these are cut is they are cut by 30-degree angles, and we're going to add 30 over and over again. Here we go. 30 plus 30 again plus 30 again. So this is the cut where I go a third of the way through a quadrant at a time, plus another 30 degrees is 120 degrees. Plus another 30 degrees is 150 degrees. Plus another 30 degrees takes me to 180, which we're going to now call a quadrangle. It's an angle on a quadrant edge. Yeah, they really did make up that word. Then another 30 degrees past 180, 210 degrees. Another 30 degrees, 240. Another 30 degrees takes us to 270. Another 30 degrees, we have 300. Another 30 degrees, we have 330 degrees. And if I go 30 more degrees, woo, back to 360. And I can keep going around if I want. and say plus another 30 takes me to 390 degrees. And I could keep going and going and going. In the same way, I could go the negative direction. If I go the negative direction, then this is negative 30 degrees. This is negative 45 degrees. This is negative 60 degrees, negative 90 degrees, and I can just keep going backward and get all my negative angles. So realize how powerful this is. Every angle that is a multiple of 30 degrees or 45 degrees, you now can find the sine and the cosine of that angle. For example, 210 degrees. If I asked you what is the cosine of 210 degrees, you would find where is 210 degrees, and then ask what is the x-coordinate of that point. The x-coordinate of that point is negative root 3 over 2. Now, what that also means is if you are at, say, 205 degrees, you're between, the cosine is between negative root 3 over 2 and negative 1. So these give you reference points, but there are plenty of other angles out there. If I looked at 210 degrees but asked you what is the sine, then after finding 210, you would look at the y-coordinate and go negative 1/2. And that's correct. Now, what I'm doing right here is I'm creating like some training wheels for the unit circle for you. Horizontal lines focus on y-coordinates. Y-coordinates are which trig function, sine or cosine? Wait, why did you write the only place I want to go is back to math 1? Okay, sine is the y-coordinate. Use horizontal lines when you are dealing with sine theta or when you are dealing with sine's reciprocal. Which function is sine's reciprocal? Cosecant. So if you need to find the sine or the cosecant of any of these angles, you're going to look at horizontal lines and see what the y is equal to. Because if you can find the sine of theta, all you have to do is take that number and go 1 divided by that number, and you've got cosecant. Vertical lines. Vertical lines focus on x values. So which trig function uses x? And I see people just about to type it. Cosine theta. Who is cosine's reciprocal? Secant. And then finally, lines through the origin, focus on slope. I want you to look at all of these blue lines. Each of these blue lines has a slope. What do you know slope happens to be? Think about what you know about slope. Slope is change in y over change in x. Oh my goodness. Are we really at 5 minutes left? Okay. I'm realizing that I cannot do this particular unit in 1 hour. So, thinking about it, I'm going to leave you here for a moment. I'm going to have to allow myself to get behind a little bit. I'm going to stop